Hello, thank you for this opportunity to present our work in the LISA Symposium. So Camille and myself will present you a study on the formalism for the new channels for the triangular gravitational-wave interferometer in the case of identical and non-identical correlation. We have studied our study in this paper. So here we are using the same configuration as LISA, A, E, and T from X, Y, and Z. Because LISA and ET will have a lot of sources, this is difficult to have an understanding of the power spectral density. For that, we have developed a method based on the formalism on the channel A, E, and T. If you switch. So the formalism is given by, for this case, identical sources, identical noise for X, Y, and Z. So we have two independent terms. So SEG from the SXY, XZZ, SYZ, and also for the PSD, SX, SY, XAZ are equal to SI. So the T channel, the node channels without gravitational wave, is given by the sum of these two components. The A and E are identical and given by the subtraction between the power spectral density and the CSD terms. We have studied this case in the case of isotropic stochastic gravitational background, this SH given by with the coefficient 9/20. In this case, you have no cross term in the channel T and A and TE and A and E. So there is no term for this component. If we use the non-identical noise for unique noise in X, Y, Z, you have the same formalism, but with new terms. So for example, if you focus for now in the T channel, you have three terms for the PSD, SX, SY, AZ, not identical, and you have also cross term, SXY, SXZ, and SYZ. Now the channel E and A are not identical. You have for A only term with X and Z, and also a gravitational wave isotropic terms. For E, you have a function of X, Y, and Z, and also the cross terms. And we have not equal to 0 for TA, TE, and A and E. In the term of T and A and T and E, there is no gravitational wave, and also a sum of the two term of the PSD and two term of the cross term. This is the same for A and E. In the case of isotropic stochastic gravitational background, there is no sources in the cross term A and E, but for other sources, gravitational wave sources can appear in these terms. Let's switch in T and T terms. In these terms, you have 6 independent sources, so X, Y, and Z, plus the cross term. But we can, from this, calculate 3 new channels. We can cross term the T plus X, the T and Z, and the T and Y. For that, we will have only 3 terms for each subterm. For example, if you focus for now on T plus X, you have the PSD of X plus the 2 terms of the cross term between SY and SZ. This is easier for an algorithm to have these 3 new channels to fit well the 6 sources. Yes, so I give for now the head to Camille.
Yes, thank you very much, Guillaume. To briefly summarize what Guillaume said, so we want to know our PSDs, our noise sources, either in the XYZ or RT-AET domain. So we start from our XYZ time data, we compute our A, E, and T channels, we move to the frequency domain. And so then the first question we are going to ask is whether we are in the identical or non-identical noise case. And so here we can use this coherence between the T and A and T and E channels, for instance. And if this is 0, you know that your noise terms in your XYZ interferometers are identical, and you're in a more simplified case. If this is non-zero, your noise sources are non-identical, and you trying to understand all these 6 terms as X, as Y, as Z, and the equivalent cross terms. And so we can use the null channel to try and estimate all these parameters, but better is to also rely on the TX, TY, TZ channels, as Guillaume mentioned, where you keep more information about which parts of the PSDs and CSDs are unique to these 3 different interferometers. So in our paper, we applied this to a toy example for the Einstein Telescope, but it's very similar for LISA. So here we have our Einstein Telescope noise curve, and what we did was injected 3 Gaussian peaks at 10 Hertz, 50 Hertz, and 90 Hertz, but we only injected 2 peaks in every interferometer in a correlated sense. So X has a peak at 10 Hertz and 50 Hertz, and then we permute these peaks such that there's always 1 peak and exactly 1 peak correlated between 2 channels. And this, of course, gives noise sources which are unique to the 3 interferometers. Then if we move to the AENT space on the right-hand side, you see the peak showing up in your AENT channels with various levels of contribution. And then if we apply our formalism here and we assume we know these Gaussian peaks and how they look like, what remains if we subtract them is exactly our Einstein Telescope noise curve from which we started. And so by applying this formalism and in the end rather modeling your Gaussian peaks, you can try to understand your entire spectral density curves, which you then can use in your gravitational wave analysis. And so as soon as your noise sources are unique, which is something you can learn from your coherence between the TA and TE channels. So if there is significant coherence, as here at the 10 Hertz, 50 Hertz, and 90 Hertz, this is an indication that your X, Y, and Z interferometers have different noise sources. And so then you can use the CSD between these T and A and T and E channels to get more information on your non-identical noise and try to understand these terms better. And so also indicate what's that the correlation between T and X might be a better model or parameter or information rather compared to the T channel. Okay, so the T channel has a combination of the X, Y, and Z interferometers, and so it contains all these 3 Gaussian peaks. But if we look at the TX channel, where we have renormalized it such that it's at the same level of your T channel, you see your PSD curve of the Einstein Telescope, and only 2 Gaussian peaks show up, and not one at 90 Hertz. And so by using these TX, TY, and TZ channels, you can keep more information about which peaks or which correlated or unique noise is present in the different interferometers. And so it will make it easier to understand the unique noise sources in the different interferometers to then model these and estimate those. So what we presented in our paper and in our presentation today is on the left-hand side, the formalism you can use to get a sense of all these noise parameters, non-identical and correlated noise. But where we really want to end is a Bayesian PSD estimation framework where we can model all of these parameters and without or with limited prior knowledge, estimate all these parameters. What we need more information about are realistic noise sources for both for the Einstein Telescope as well as for LISA to really understand which noise sources can couple, are correlated between our interferometers and might affect our searches. Also interesting is to understand which sensors might be available measuring these correlated noise sources, so you can have additional information constraining your parameter space you need to model by cleverly using this additional information in your framework. And then a final item to further understand is the interplay between the dimensionality of your problem and the non-stationarity. So there are a lot of parameters that need to be fit for all your different noise sources. So on the one hand, you want to use a lot of data to model these parameters to decrease your uncertainty. But on the other hand, this won't be, you can't stretch this to extreme long times, because then non-stationarity of your noise sources and of your data will show up, and your parameters might fluctuate over time. So you have to keep it short at the same time. And so finding the optimal sweet spot is another interesting study point. But then in the end, we will arrive at the Bayesian PSD estimation framework, where we can model all our noise parameters. So what we presented here today is how we can use the A, E, and T channels, where non-identical and correlated noise in the X, Y, and Z interferometers is present, and which information can be gained. And so you can use the correlation between the TX, TY, and TZ channels, because they keep some more information about the unique noise sources in the PSDs of the X, Y, and Z interferometers. We also showed that the coherence between the T and the A and E channels is an important indicator whether there are unique noise sources and non-identical behavior between your X, Y, and Z channels or not. And if that's the case, you can use your CSD to gain some more information about those. And we used a simple toy example for the Einstein Telescope to demonstrate how this can be used. And then the next natural step is to really start building a Bayesian estimation framework to estimate your noise parameters, and slowly adding in more realistic and complex correlated noise sources to understand how it might affect your analysis searches. So with this, we would like to conclude our presentation, and thank you very much for the opportunity to present it here today.